has made his PhD not far from here, with Emmanuel Dormy at Normal Superior Prix-Lomond, and he's now EAMTP in the University of Cambridge in the UK, and he will talk to us about breaking water waves and the limit of vanishing viscosity. Please, Alan.
Thank you for the introduction, and thank you for inviting me to give this seminar here. Good morning, everyone. Yes, I will tell my work I did during my PhD is focused on breaking water waves, and so it's good to start, I think, with small definitions and a few observations. So here you see a video I took in Bretagne, in Finistère. And the thing you can observe is that when you look at the surface of the ocean very far from the shore in the deep open ocean, it's a good idea to represent the interface between air and water as the graph of a single valued function. But when you observe the ocean in the vicinity of the shore, in the beaches, for instance, then you see an instability that arises and which results in the breaking of the wave. We say that the interface overcurls and it can no longer be represented by a single valued function. En français, on parlera de déferlement ou de brisure. On dit que la vague se retourne, qu'elle forme des rouleaux, par exemple. Well, the thing is, we know why water waves break. We can describe the instability mechanism taking place, and I will shortly describe it as an introduction to this talk. And so we will consider a two-dimensional slice of the ocean and a wave of amplitude A and traveling in the right direction. Of course, the amplitude must be understood in a non-dimensional setting. So if you're in a shallow water regime, that is, if the depth of the fluid is small compared to the wavelength, then you can use the depth of the fluid to non-dimensionalize the amplitude. And in the deep water regime, you will use the wavelength. And so this is the deep water regime is the case when the wavelength is shorter than the depth of the ocean. And so in all cases, when the amplitude, non-dimensional amplitude, is small, then the wave evolves without breaking. But once a certain threshold is reached in the amplitude, then there is an instability mechanism that arises, and that is, there is the growth of a perturbation, and the result of this perturbation is that in the front of a crest, the velocity decreases, and the back of a crest, the velocity increases, and eventually the wave breaks. This is called the superharmonic instability, mainly because this perturbation is of the mode associated with this perturbation of higher order than the base wavelength of the wave. There are also subharmonic instabilities arising in water waves, like Benjamin Fair instability, but these cases make the amplitude rise, but they are not triggering wave breaking by themselves. So the superharmonic instability was first discovered during the late 70s by Longuet-Higgins and Coquelet, and to do so, they used the first numerical method to study breaking water waves. It was based on Euler's equation, assuming irrotationality, but they managed to do it. And it was later confirmed by the work of Tanaka, which extended it to the case of non-periodic wave trains like solitons. And more recently, in the work of Mansart, Turner, Bridges, and Diaz, they included the effects of viscosity and surface tension to see if the same mechanism still arises. So this is about the history of why wave breaks. And the thing I would like to note is that the study of wave breaking as a phenomenon is entangled to the use of numerical simulations. And I will use numerical simulations. I will present that today. So when you look at the literature about wave breaking, you can see two different approaches. The first one I will call geometrical, in which people are more interested in describing the shape of a wave that has broken. Most of the time, they use an explicit interface representation. That is, the interface can be seen as a parameterized curve or surface in 2 or 3-dimensional space. And this surface is advected in a Lagrangian manner. Other people use what I would like to call the phenomenological viewpoint, and they are interested not exactly in describing the shape of the wave, but more about what happens after what's called the splash singularity. So the splash singularity is the moment the interface intersects itself here, for instance. And the thing is that most geometrical studies fail to describe the post-splash mechanisms. However, once the splash singularity has occurred, there are a lot of small-scale vortical structures that arises. Vortices, filaments, turbulence in a way, and so turbulence with energy, the associated energy dissipation. And of course, people using the phenomenological point of view are sometimes more interested in describing this energy dissipation and trying to come up with empirical models for that. In my case, I will use the geometrical viewpoint, but I will use equations that are usually employed in the phenomenological viewpoint. As you will see, this will, in a sense, conciliate the two approaches, but it has all the difficulties the first one can have, in the sense that it won't work after the splash singularity. Okay. In particular, I would like to discuss the vanishing viscosity limit. This is very theoretical, but it's also quite useful when you want to come up with a reduced model for ocean dynamics, for instance. So the vanishing viscosity is basically, can you use Euler's equation instead of Navier-Stokes equation? Are the viscous effects negligible? Or, in other terms, is there turbulence arising in the flow? And why is it interesting to know when you can use inviscid models and when you cannot? Well, the thing is that from Euler's equation, you can derive asymptotic regimes that are way easier to work with. For instance, we all know the Saint-Venant systems, that is the shallow water equation. This equation can be mathematically rigorously proven to correspond to shallow asymptotic regimes of the free surface Euler equation when there is no breaking happening. We can think also of the Boussinesq equation, Serre, Green, and Nagdi equations, KdV. All these reduced models correspond to shallow asymptotic regime, that is, the wavelength is supposed very high, very big compared to the depth of the fluid. But there exist also other asymptotic regimes corresponding to deep water regime in which filtering is applied. If you do so, you obtain, for instance, the nonlinear Schrödinger equation at first order, and at higher order, you can get the Dist equation. There exist many other asymptotic regimes, and they are all based on Euler's system, that is, we forget about the viscous effects. There exist also some reduced models based on the Navier-Stokes system, but most of the time their derivation makes strong hypotheses regarding the shape of viscosity in boundary layers. So, if the first limit, taking Navier-Stokes to Euler, actually holds, in that case, you can maybe use one of these reduced models and simplify your life. But is it always the case? Well, I would like to discuss that today. So I will talk about the vanishing viscosity limit up to the splash, because of course after the splash there are turbulence, and so we know vanishing viscosity won't be a good hypothesis. So at first I will describe a numerical method to solve the free surface Navier-Stokes equation in the presence of a breaking wave, and up to the splash singularity it will use a mesh advection scheme and finite elements. And then I will use this numerical method in order to study boundary layers appearing in water waves. So there are basically two boundary layers in water waves, the one lying near the free surface and the one lying at the bottom. And so I would like to discuss both of them during this talk. So let's start by describing the numerical methods we came up during my PhD. So it's a bit different from what you're used to, and I would like to emphasize that by giving you a short history of numerical works regarding breaking waves. So as previously mentioned, it all started during the late 70s with the work of Longuet-Higgins and Coquelet, which mapped the two-dimensional flow into the unit circle in the complex plane. It was another method which makes use of the complex plane and so are intrinsically two-dimensional, all the vortex and dipole methods introduced by Baker, Mayron, and Orszag at the beginning of the 80s. And the idea behind this method is to assume irrotationality of the flow and use the velocity potential. And then you can reduce the intrinsic dimension of the problem by 1. That is, if you have a two-dimensional flow, you can obtain a one-dimensional set of equations, which makes numerical resolution easier. These methods have, for instance, been used by Baker and Xi in 2011 to come up with an initial condition that eventually formed a finite time cusp-like singularity. That is, starting from what's initially not a cosine wave but close to it in a periodic domain. In finite time, you get a breaking wave that shows an angle here. And so that is the curvature of the interface eventually blows up. I believe that this numerical study should be confirmed using other numerical methods, but it's a very good start for a conjecture that's long-standing in the applied math communities. And more recently, Dormy and Lacave came up with a mathematical, rigorous justification of this formulation, the vortex and dipole formulation based on irrotational Euler's free surface system. As I previously said, these methods make use of the two-dimensional complex plane, and therefore you must lose this hypothesis if you want to go into in three dimensions. And this was done, for instance, by Riquier, Guyen, and Diaz, using the boundary element method at the beginning of this century. Other methods were used, but are based on the Navier-Stokes system and use DNS basically of the flow. The thing is that now you cannot reduce the dimension of the system, and therefore you must solve the full 2D or 3D equations, and so we had to wait for the computational power to make this kind of numerical work. One can think of the work of Shen, Karif, Zaleski, and Lee at the end of the previous century. And in 3 dimensions, you have the work of Lubin and Glockner, and of course using Basilisk software, like in the work of Dake, Melville, and Popinet, or many more recent studies, for instance. In my case, I will try to solve the Navier-Stokes equation numerically, but using methods that are usually used in the Euler irrotational community. We will see how to do that, and this will allow to increase Reynolds number and compare the solution up to the splash with the irrotational solution computed using the dipole method. But I won't talk about this method here. You can ask me some question afterward. So we will solve the Navier-Stokes equation, and to do so, in order to reduce the number of parameters, we will non-dimensionalize the equations. The characteristic length chosen is the average depth of the fluid domain. That is, we are in a shallow water regime. And the characteristic velocity is the leading order velocity of the Stokes wave in shallow water. We end up with this Reynolds number should we do so. But since there are many characteristic lengths and velocities in this problem, we could use other Reynolds numbers. For instance, some people prefer to use the deep water Reynolds number, in which h0 is replaced by the wavelength lambda. This yields a bigger Reynolds number than the one considered here, because in our case, lambda, the wavelength, is bigger than the height of the domain. Should we do so, we obtain the incompressible non-dimensional Navier-Stokes equations that we would like to solve in the fluid domain, which corresponds only to the water. Indeed, we neglect the air whatsoever, mainly because the asymptotic model, Euler system, has troubles when you include the air because of the Kelvin-Helmholtz instability that can arise. And so for now in this work, we neglect the effects of the air. We are periodic in the horizontal direction and two-dimensional whatsoever. Regarding boundary conditions, on the free surface, we impose what's called the stress-free boundary condition without surface tension. We could include surface tension, but we are interested in the viscous effects in this study, so we discard it for now. So it basically says that in the normal direction, the stress tensor is continuous through the interface. But since there is no upper fluid, the stress tensor vanishes in the normal direction. And at the bottom, since for now we will be interested only in the surface boundary layer, we do not want any boundary layer at the bottom, and so we will use the slip or Navier boundary condition, non-penetrability of the bottom, and vanishing shear stress, so that in the flat case, there are no boundary layer appearing. The initial condition is irrotational, and this is very important because we will compare our results with the irrotational Euler solution, so inviscid, which will remain. In the inviscid case, of course, irrotationality is preserved because of Kelvin's circulation theorem. And so in our case, to obtain an initial irrotational condition, we will use the velocity potential that I call phi 0. And it is computed numerically by solving Laplace's equation in the fluid domain with the non-penetrability condition here, and we prescribe the initial velocity in the normal direction. How can we do that? Well, we use the velocity computed from the leading order Stokes wave solution, that is basically a cosine wave with a cosine velocity and sine velocity depending on the horizontal and vertical component. One thing just to note is that usually when you do the analytical work to obtain this solution, there is the vertical component in blue here, but here it is replaced by the average value of the vertical component, which is the depth of the fluid domain. In this way, the initial condition is symmetric, meaning that the velocity norm on the crests is equal to the velocity norm on the troughs, and in that case we obtain better looking results. But this is not exactly the linear solution, but the linear solution being only valid for small amplitude, this is not really a problem here. We want to use finite element discretization. So we must come up with a weak formulation of the problem. How to do that? Well, you take your Navier-Stokes equation and you multiply the momentum equation by any function v, of course, a vector valued function v, and integrate over the fluid domain omega. You do the same for the incompressibility condition. You multiply it by a scalar function q, and you integrate over omega, add the two terms, and you obtain, after making use of the divergence theorem, you obtain this. So the thing is, you use divergence theorem on the viscous term, and you come up with the symmetric part of the gradient of both the real velocity v and what's called the test function, the real velocity u, and what's called the test function v. And also see that there is no longer the gradient of the pressure because of the integration by part. We instead see that we have the incompressibility condition applied to the vector test function v, and also the incompressibility condition applied to the test function, to the velocity u. So in that case, P and Q can be seen as Lagrange multipliers, ensuring the incompressibility of the flow. So this is the weak formulation you can use to solve the problem using finite elements. Should you want to include the surface tension effects, you would get another term here, which is a surface integral on the free surface. You have kappa, the curvature of the interface, and Bo, which is Bond's number, which appears through non-dimensionalization of the surface tension coefficients. In our case, we will take Bond equal infinity so that this is 0, and we will only focus on Reynolds number. Okay. One last thing about the formulation, we want to move the interface in a Lagrangian manner, meaning that we represent the free surface as a parametrized curve in two-dimensional space. So t is the time, s is the parameter, and each point lying on the surface moving with the fluid, we are Lagrangian. We use the Lagrangian equation, which basically says that the velocity of the point with parameter s is exactly the fluid's velocity taken on the interface. We will see how to implement this when you have a full mesh to move later. Implementation is made using FreeFEM. FreeFEM works quite well in 2D, but in 3D difficulties arise, and so the simulations I would like to discuss today are two-dimensional. For this reason, we are currently working on the three-dimensional code, but using something different than FreeFEM. FreeFEM allows to generate and handle the mesh, but also the matrices. And we can use PET-C because it has an interface in FreeFEM in order to make the code multi-threaded rather easily. So as you see, we only compute an unstructured mesh in the bottom fluid, since we discard the effects of the air whatsoever. So this is, for instance, the initial mesh. Now the question arises how to move the mesh so that you move the free surface. Well, there is a method that exists, and it's called the ALE method. Schematically speaking, it works like this. Consider a mesh at time t. We will define another velocity called w, which does not need to be the fluid's velocity. It is arbitrary. And then at each time step, the mesh is advected with this velocity w. This is called the arbitrary Lagrangian Eulerian method, ALE. In our case, the arbitrary velocity W is computed by numerically solving the following elliptic problem. So this is Laplace's equation, the vector Laplace's equation actually in the domain. But the interesting thing, I believe, are the boundary condition. We take W equal the fluid's velocity on the free surface, that is, we are Lagrangian there, and we take W equals 0 on the bottom, that is, we are Eulerian there. And in between, we are a mixed Lagrangian Eulerian method. You now understand the name of this scheme. Putting everything together, we used a backward Euler implicit scheme for all terms, but the nonlinear one because we want to prevent the use of a nonlinear solver, and so the nonlinear term has an implicit scheme here and an explicit one here. Also notice that since you're technically working in a moving frame, you must subtract the mesh's velocity in the transport term here. And you see that if, for instance, you use the fully Lagrangian viewpoint, in that case, Wn is equal to Un, and the nonlinearity in the Navier-Stokes system completely disappears, which is quite good, but it reappears in the mesh advection scheme. So I don't know if it's really a good idea. I am currently trying to do that. So this is about the time-stepping scheme. Now about a few points about multi-threading. So the thing is that when you want to parallelize your code, well, one of the things you can use is domain decomposition method. The idea is as follows. You take your domain and you segment it into many subdomains, and each MPI core takes care of only one domain. So each color corresponds to one core, and in the case of 6 MPI processes, so very low. And you see that since we are periodic in the horizontal direction, the same MPI core takes care of the right and left boundary. The thing is that when you increase the number of MPI cores with this method, it takes longer and longer to converge because the information takes more and more time to travel from one domain to its opposite at the other end of the physical domain, if you want. So in order to increase the convergence rate, what you can do is use geometric multigrid preconditioning. The idea is to have multiple grids, a very fine one, but also coarser and coarser ones. And it's very easy to solve the problem and very quick to solve the problem on the coarser one. And so you use the coarser to make the information travel fast between subdomains. And then you iterate in order to go to the final level and get the wanted accuracy for your method. So this is about how the code works. Now let's use it to investigate boundary layers appearing in possibly breaking water waves. So here is a sample result. It is a numerical simulations at a Reynolds number 10 to the power 6, so 1 million. This is the highest value we were able to achieve, and we were able to achieve such high values mainly because the flow up to the splash is not turbulent, and so there are not very precise vortical structure, and we can use such high values of Reynolds number, which is a good thing because we want to compare our results with the inviscid solution. Also notice, of course, that the numerical method fails once the splash singularity has arisen. I would like to show you the mesh during these kind of simulations because we implemented mesh adaptation in order to have very coarse, very big triangles when there is no need to have very precise things, that is, when there is no vertical structures to resolve numerically, and very large amounts of triangles near the free surface, because there may be a boundary layer appearing and we want to resolve it. And of course you see that the free surface moves but the bottom doesn't. So now that we have a numerical method that works for the Navier-Stokes system, we can compare to Euler's inviscid irrotational solution approximated using the dipole method implemented in the work of Dormy and Lacave. So this is the dashed black line here, the Reynolds equals infinity, and we gradually increase the value of Reynolds number throughout the simulation up to the highest value, Reynolds equals 1 million. We see that the most viscous case, Reynolds equals 10 to the power 2, becomes different quite rapidly. But as the time increases, as the simulation the simulations go on, we see the convergence to Euler's irrotational solution. So here is a snapshot before the splash occurred for the most viscous simulation, and we see that as the Reynolds number increases, the shape of the free surface gradually tends to the irrotational solution. And if I zoom in here, we see only a very small gap between the irrotational and the viscous, but with a very low viscosity numerical solution. But is it really a good Reynolds number for real life breaking waves? Well, the thing is, in the ocean you have you can have very, well, I can't say that, but in the case of the ocean, Reynolds equals 10 to the power 6 corresponds to waves of about, in our case, about 50 centimeters deep. So very small, right? We would like to go even higher and consider a few meters high, deep water column. But in that case, the Reynolds number would be 10 to the power 7, to the power 8, to the power 9, even in deep water current. And so we did not achieve real life values of Reynolds number, but we still see convergence in that case. And if I go just before the splash, once again you have to zoom in quite closely to see the gap between this simulation and the inviscid one. Of course, these observations can be made precise and rigorous using, for instance, a way to compute the distance between two curves. This is called Hausdorff distance. I can talk about that if you want, but I won't discuss that here. This is very technical. So we can conjecture the convergence to the inviscid solution up to the splash in that case. But to understand why we can do that, it's interesting to see the vorticity. First of all, the vorticity will tell us if there is a boundary layer that appears here, but also computing the vorticity gives us insight about the viscous dissipation. So of course, when you do fluid dynamics, you can take the kinetic energy equation, here phrased in two dimensions, and you see that the viscous dissipation appears when the vorticity is not zero. We say that viscous dissipation appears in the support of the vorticity, mathematically speaking. And you can also understand the vorticity generation by the free surface by just taking the stress-free condition, keeping only the tangential part, and making some algebra. You obtain an equation for the generation of vorticity. So the vorticity is generated by two terms. the first one is very important. You see that there is kappa, the curvature of the flow, and the tangential velocity. That is, strong vorticity is generated when there is very highly curved interface with a very strong surface current. Is it the case here? Here is a plot of the vorticity. It's green when the vorticity is 0, and yellow or blue when the vorticity is not 0. And what you see is that, first of all, the vorticity remains 0 almost everywhere, but in a fine sheet lying in the vicinity of the free surface. And it arises in this region. It's become clearer afterward. Vorticity tends to be concentrated here. And this is because we have the curvature of the interface that increases there, and also there is a strong surface current. You can feel this surface current when you swim in the water. When there is a wave approaching, you get somewhat there is a current that makes you swim into the wave as the wave approaches you. So this is the Reynolds equals 10 to the power 3 simulation. I will show you the other simulations, but the vorticity sheet becomes thinner and thinner, and we wouldn't see anything else. So I will need to zoom in more closely to see the vorticity sheet. So this is what I do here. At Reynolds equals 10 to the power 2, power 3, 4, 5, and eventually 6. And what we see, so now the vorticity is 0 when it is yellow. Sorry for the change of color map. What we see is that the vorticity sheet gets thinner and thinner and thinner. And to know if it's really a boundary layer, we must investigate its scaling. To do so, we come up with vorticity cross-section along the black lines that are shown here. They are taken in a normal direction, and we plot here the vorticity along these black lines. And what we see is that, so of course, in that case, S is the arc length of the vorticity cut, with the 0 taken near the interface, and it is rescaled by the square root of the Reynolds just to see if it follows the usual boundary layer scaling. And what we see is that, yes, Reynolds equals 10 to the power 2 didn't achieve its asymptotical regime yet, but the other simulations show the boundary layer scaling, the usual one, as 1 over the square root of the Reynolds number, as the square root of the viscosity, if you want. And also we see that the highest value of the Reynolds number is not fully resolved. As you see, this is only one triangle here, and so, but we were not able to increase even further the number of triangles on the interface without the simulations taking a very long time and having instabilities arise also. So this is a boundary layer, but of which type? Because you see, the vorticity is also uniformly bounded. That is, when you have, for instance, a boundary layer, a Prandtl-like boundary layer, you know that the vorticity, the size of the vorticity sheet decreases as 1 over the square root of the Reynolds number, but also the vorticity blows up at the same time. This is not the case here, because this is not a Prandtl-like boundary layer. This is what's sometimes called a Navier boundary layer, with bounded vorticity that doesn't change in absolute value when you increase Reynolds number. And using that, we understand the convergence that we exhibited before, because the vorticity is uniformly bounded and in a thin sheet that progressively tends to 0, and hence the vorticity tends to 0 as the Reynolds number is increased. And so we in that way we understand the convergence that we saw before. So this is about the surface boundary layer. Now in the remaining time I would like to discuss the bed's boundary layer. That is the boundary layer that can appear at the bottom of the ocean. To do so, we will replace the slip Navier condition with the no slip condition, and we will add at first an obstacle that is basically a rectangle here. And should we do that, of course I will now take a very small amplitude because breaking is not what's important here. And so in order to prevent wave breaking to arise, I will take a very small amplitude. And should we do that, we obtain this convergence or non-convergence figure. So once again, this is Euler solution in black, and we gradually increase Reynolds number up to Reynolds equals 10 to the power of 5 now. Why not more? Because as you'll see, there are very large velocities, and so due to the CFL condition, large velocity mean a very small time step, and the simulation take a lot of time. But what we see is that the Navier-Stokes solution gradually tends to something that is not Euler's irrotational free surface solution in black. Instead, it seems to tend to something else. We can make that precise by computing the L2 distance. So this is the distance to the Euler solution with time, and this is the distance to the highest Reynolds number solution also with time. And what we see is that the distance to Euler solution gradually increases, but at the same time the distance to the highest Reynolds solution seems to decrease. And so we seem to have a convergent sequence of solution, but it doesn't converge to Euler's irrotational one. And why is that? Of course, you may have guessed it, boundary layer separation. So what we see here is that, so this is the vorticity once again, and what we see is that in the vicinity of the corners of the rectangle, there is separation appearing. This separation takes the form of vortex filaments, and due to the Kelvin-Helmholtz instability, these filaments rolls up on themselves, and the final vortical structures look like pairs of vortices. You can see them here. And eventually these pairs of vortices are advected towards the interface and perturb it in a singular fashion. That is, in a way that does not decrease when you decrease the viscosity, unfortunately. So the question is, should we increase the Reynolds number even more? Should we get a turbulent flow? Well, maybe, but for now we do not get it. We only get pairs of vortices in a sense. So this is a simulation with a Reynolds number equal 10 to the power of 3.5, power of 4, power of 4.5, and power of 5. And what we see is that the vortical structure remains coherent when we increase the Reynolds number. So why pairs of vortices? Well, to understand that, we can show the streamlines of the flow. And so those are the streamlines shown in the vicinity of the right corner. And what we see is that before the crest passes above the corner, the flow looks like a well-known solution of potential theory. That is, the solution when the streamlines wrap around an angle like this. Then when the crest passes above the obstacle, then the streamlines change direction, and the separation takes place at this exact moment. That you see there are streamlines coming from the bottom and streamlines coming from the left. A bit like what you see in the vicinity of the aircraft's wings. yes, in that case, so if this is an aircraft's wing, the streamline go like this, and so you can basically think that this is the same mechanism, and we know from basic boundary layer separation theory that in that case we get a sort of von Karman vortex street like that. And this is what we see here. But since the flow is oscillating, we get at first a positive vortex detached, and then a negative one. And then once again the streamline are reversed, and so you get a positive one and then a negative one, and so on and so on. And this is why you get this kind of vortex pairs being emitted in the vicinity of the corner. So of course, having boundary layer separation when you have such singular obstacle is not very surprising. But what happens when you get a very smooth obstacle? Well, to build such topography, we can use the method of mollifiers. The idea is as follows. If gamma b is the parametrization of the topography, which is singular in our case, we can define a smooth version using convolution. So the smoothed version is called gamma b epsilon, with epsilon the curvature radius of the topography near the corners. And it is defined by convolution with a convolution kernel that is defined from what's called a bump function, like this one, for instance. So this is a function whose integral is equal to 1, which is positive, and which, as epsilon goes to 0, tends to a Dirac delta function. But in our case, we won't let epsilon go to 0 because we will think of epsilon as being the curvature radius of our step. We obtain this kind of result. So this is for the small value of epsilon, very small curvature radius, very highly curved obstacle. But once again, this is smooth. And we still see boundary layer separation appearing. But if we increase the value of epsilon, if we decrease the value of the curvature, then the separation eventually stops. So at fixed value of the Reynolds number, there seems to be a curvature threshold above which separation starts. Or taken the other way around, at fixed curvature, there seems to be a Reynolds threshold above which separation starts. This is not very surprising, but in that case, for non-flat bottom, we know that the vanishing viscosity limit won't work, and that there will be a singular perturbation that will arise and which will prevent us to use any kind of reduced models that are based on Euler's irrotational solution. If we want to understand the underlying separation mechanism, once again, this is because of the streamlines that are reversed when the crest passes over the obstacle. So this is about my conclusion to my talk, and I would like to thank you for your attention.
Very much for this very interesting talk. Any questions? Okay, we'll start with the question. So just for your final remark on the separation that is modified. I think there's a theory by Stewart-son that he calls the 1/4 exponent of the Reynolds number.
Yes, for an angle, not a smooth one.
Okay.
Yes, I know that.
Yes,
Thank you very much. That's very nice work.
I use the microphone online.
So you mentioned the geometry of the geometry. So and you also mentioned surface tension at some point. So how do you think this picture would be modified if you had surface tension?
Oh, you mean in the case of the free surface boundary layer, like this one? Yes, we should try it. We expect, of course, at some point the surface tension will tend to regularize, so increase the curvature radius of the free surface. And so in that case, because of if the curvature is decreased, we know that the vorticity will be smaller in volume.
But you could have the other effect, because you will have generation, or you can have, depending on the regime, generation of small-scale capillary waves.
Yes, of course. Yes.
And they actually generate.
Yes, using this mechanism. There is a paper by Longet Higgins about that.
Both ways, right?
Yes,
Exactly.
in a way.
The peak, but at the same time, it can generate more vorticity.
Yes.
Where
Yes, you're right.
Yes, to rebound on that, if the vorticity separates, you will have some random vortices under the waves, and eventually you could argue that on the surface you have a layer of turbulence flow. How would that turbulence interact with the approximate potential solution that you found? For example, could a vortex colliding with the free surface create more vorticity separation? Or have you looked at that? What happens if a vortex pair, for example, hits the surface?
In the simulations I showed, vortex pair eventually come very close to the surface, but they do not reach it. But of course, it may happen if, for instance, the topography becomes closer to the free surface, I believe. But I don't know about any study that did that. And also, in the case of turbulent flows, we should, of course, go to 3D to check that, because two-dimensional turbulence is not very interesting, right?
One thing that could happen is that turbulence could create some kind of effective viscosity that could make the boundary layers thicker.
Ah, yes, in a way.
The other one thickness. And so that would destroy the potential flow. I mean, this is an argument I had with some people in the wave community, some more maybe on the ocean engineering side, and they insist on computing water waves using turbulence models. And I tell them, no, you shouldn't use turbulence models because, as people like you have nicely shown, the flow is potential. So you don't need a turbulence model. But they say, yes, there is turbulence. So, and it's a little bit of a mysterious debate for me. A small historical point. I'm happy to see you have cited the PhD thesis of Paul Gang-Chen under Christian Carif and me. But about at the same time, there was very nice work by Moonverdi and Tripperson, I think, also using Navier-Stokes in 2D. It was really nice work. They didn't go to the breaking stage, but they looked at the waves. Very nice way.
I should check that.
It's also related to move from Euler to Navier-Stokes. So you mentioned the boundary element methods and the models which can include a model of the boundary layers, right? So you can have viscous corrections to the.
Yes.
Did you try to compare, for example, your results and see, for example, how well these models do at modeling the boundary layer? Because, of course, in your case, you have the direct results for that. So I think it would be interesting to see the validity of this simpler model.
Yes.
But including some.
Yes, the thing we are trying to do is actually adding point vortices in the flow and see if this reduces eventually the gap between Navier-Stokes and Euler plus point vortices difference. But of course, we could also add the like some sort of yes, not really a boundary layer, but like you said, and manually this boundary layer to see if it actually changes something. We will do that, I believe.
Yeah. Thank you again.